Okay, so I'm going to do a comparison right now between the heat of formation and heat of reaction method. I'm not going to plug any numbers in, but I want to just really drive home the point that these are mathematically exactly the same approaches. Then I'm going to work through an example of how we set up these calculations on the computer that'll help you be able to knock out the project and homework 9. All right? So let's try and hammer through these. So this one is going to look like a familiar reaction. This is the steam reforming reaction. Okay? And we're going to solve this process using both the heat of formation and heat of reaction method symbolically, and then we're going to show how they're algebraically identical. Right? So the temperature of this reaction here is going to be isothermal at 1,000 degrees C. So when I have an isothermal reaction occurring, I can actually phrase this in a different way. This is just the heat of reaction at 1,000 degrees. I am reacting methane and water to form carbon monoxide and hydrogen. If this goes 100% to completion in the stoichiometric ratios, the heat in and out of this process is the delta H of reaction. Right? So this Q here would be equal to the delta H of this reaction at 1,000 degrees Celsius. I don't know the heat of reaction at 1,000 degrees Celsius. I do know the heat of reaction at 25 degrees Celsius, right? Because that's where we measure all of our energies of formation. So we have two approaches. The heat of reaction approach, Q is going to be equal to the extent of reaction times the heat of reaction at the standard state minus the summation of the enthalpies out, plus the summation of the enthalpies out minus the summation of the enthalpies in. The heat of formation approach, Q is going to be equal to just the summation out minus the summation in. All right? Question?
Out and in, is that just products and reactants? Or
Yes. Products and reactants, or this could be a process, right, where we have a box, right, and we're flowing stuff in and out of the system. Or the box could be time. This could be initial and final. Right? So this could be a closed system at constant pressure. This could be a continuous steady state process. The math is identical. The only difference is that for a closed constant pressure system, instead of n dot, it would just be n. Right? So you wouldn't have a per unit time. Yes?
So this is calculating like the heat that is the Q that we're calculating. This is the heat that's being made from the reaction, right?
Made or released. Well, so energy is not being created or destroyed. What's changing is how much energy the carbon-hydrogen bonds can hold versus the oxygen-hydrogen bonds can hold compared to how much these bonds can hold. Right? So at a certain temperature, those bonds all contain a certain amount of energy. And if there's an imbalance between the energy of those chemical bonds, that has to go somewhere. In an adiabatic system, it'll heat or cool the system down. In an isothermal system, heat will be removed or absorbed by the process. Right? So we're looking at the change in energy of the chemical bonds. Yes?
So if we wanted to find the Q that we would need to put into the system to hold it at 1,000 degrees Celsius, then we'd have to take into account this Q.
This is exactly what we're doing. This Q here is the energy that we would have to put in or take out of this process to keep it at 1,000. And that energy is exactly the same as what the heat of reaction is. So if the heat of reaction were 0, then no energy would have to go in and out. If the heat of reaction is positive or negative, we either have to put energy in or take energy out. Right? So an exothermic process gives off heat energy. That means that my Q should be negative. If this is endothermic, the reaction needs energy. That means the Q would be positive.
So we're assuming that it's already at 1,000 degrees Celsius.
Correct.
Okay.
So if this thing happens at 1,000, do I need to put energy into it or take energy out of it? And that is exactly what the heat of reaction is. Only if this is the stoichiometric ratio, which it is for this example. Okay, so our first step, before we even decide which of these methods we want to do, we're going to build a table. Right? So our table is going to consist of methane, water, carbon monoxide, and hydrogen. We're going to have a flow rate in, we're going to have an enthalpy in, we're going to have a flow rate out, and we're going to have an enthalpy out. So if we're feeding it in stoichiometric ratios, we can fill in our material balances, right? Because this is exam 1 content. And for this example, the extent of reaction is 1 mole, or 1 mole per second, right? So we have 1 methane, 1 oxygen, moving over to 1 CO and 3 hydrogens. That's 1 extent of reaction. Or if it's flowing, 1 mole per second, right? Okay, so for the heat of reaction method, we're going to solve it 2 different ways and show that they're equivalent. Yes?
So for systems where we don't know the exact composition of all the stuff, can you still use the heat formation if you need the extent of reaction?
What do you mean by that? Say it one more time.
Well, like, for example, when we were learning about extent of reaction stuff, so we went, for example, like gasoline, we don't know the exact composition of everything in the input. If you have a system like that, can you still use the extent of reaction?
No, not trivially. So for that, there's a measurement called the heat of combustion. And so we convert that to something called a higher heating value or a lower heating value. So what we do instead there is we just take the fuel, we burn it, measure how much energy comes off, and then when you're trying to figure out how much of the fuel you need to burn, you use that number. So for a complex fuel like that, no, we can't do it like this. We'd have to use a measurement of what that combustion is. And I've actually got that on schedule for next week to talk about in more detail. Yes, question? Yeah, so I just chose a basis, but we could also solve for what the extent of reaction is, right? So the number of moles of species I is equal to the number of moles of species I initially plus the stoichiometric coefficient times by the extent of reaction. So we can solve for what the extent of reaction is by Ni minus Ni naught divided by stoichiometric coefficient is equal to the extent of reaction. So if we have the mixture here that's in the stoichiometric ratio, we could plug any one of these 4 species into this equation here, and it should spit out with the right stoichiometric ratio. So let's take hydrogen, for example. We have 3 minus 0 divided by 3. 3 divided by 3 is 1. Same thing with methane. Oops, CH4, right? None coming out, minus 1 coming in. Minus 1 stoichiometric ratio, minus 1 is 1. Yes?
For this stoichiometric ratio calculation, does the input or the flows in have to be in the stoichiometric ratio? Because
No,
could put
absolutely not.
So if you put like 80 moles of CH4,
I could change these tables. Yep, I could change these tables 100% arbitrarily, and the energy balance calculations will work themselves out.
But they, in comparison to each other, the molecules have to be in their ratios, or no?
No.
Because if you did like 80 moles of CH4, but only there's only 1 made, then you're going to get a very low extent of reaction.
Correct. Yes. So we'll talk about that hopefully in like 10 minutes when I wrap this thing up. Okay. But these calculations for the enthalpy are 100% independent from the actual material balance. So you can calculate all of the enthalpies independently of the material balance. Combining the material balance with the enthalpy calculations will tell us what the Q is. But you could have partial reactions, and in fact, I'm showing an example next that has 3 different independent reactions. And showing that we can just arbitrarily throw any numbers out there and we can get the energy balance to work out. Question?
So would it be safe to, like, based on the formula there, would it be safe to say any reaction goes to completion, like doesn't have any
No.
reactants?
No, nothing goes to completion, except like combustion processes.
Well, yeah, but
I mean, some do. I mean, there's some industrial processes where you can reliably get it to completion, but there's always byproducts, there's always side reactions, there's always partial reactions. So these are idealized systems.
But for modeling purposes, if you have a reaction goes to completion, any reaction goes to completion, you can say has an extent of reaction of 1.
No, it depends on how you draw the chemical reaction too. So I could have doubled this 2CH4, 2H2O. Well, that still would be an extent of reaction of 1. Well, maybe.
Because if there's no reactants or products on nothing goes on the product side, it's on the reactant side, nothing goes on the reactant side, it's on the product side, then
I've never encountered a situation where that sort of cornerstone makes it easier. I've just always let the extent of reaction be whatever it needs to be. But maybe if you draw your reaction right and it's in stoichiometric ratios and it goes to completion, it probably does always equal 1. Okay. So I'm just going to quickly write out what the processes are. So for the reaction method, okay, now I'm not going to write each specific compound because they're just going to have slightly different properties that we can look up. In the heat of reaction method, the enthalpy value that I'm going to put into the table for in and out, all the same, right, is going to be, so first I'm going to try and calculate a delta H going from the reference state to the 1000 degrees C. So this is going to be the enthalpy of the system, like HI is not H initial, it's H of species I minus H reference, right? So I'm going from the reference state to the conditions that I care about. So reference state to 1000 degrees C. This delta H, this H is 0. The enthalpy reference is 0. That's our starting point. Okay? So I just need to get from my starting point to 1000 degrees C. Okay? So I'm starting off with all the molecules. I just need to heat them up. So that means I can just write out, this is going to be integral of C of 25 to 1000 C sub P of species I dt. And we're going to use everything in the gas phase for the formation energies. So water has a heat of formation in the back of the book for the gas phase. Okay? So this equation is exactly the same for all 4 species in the system. The only difference is what is the heat capacity. Okay? But the formula is exactly the same. All right? The only other additional thing I need is the delta H of the reaction, which is the summation of the stoichiometric coefficients multiplied by the heat of formations of all the species. So this is going to be final minus initial, so it's going to be delta H formation carbon monoxide plus 3 delta H formation of hydrogen minus 1 delta H formation of methane minus 1 delta H formation of water. Right? So now all I have to do is fill in these enthalpies, right? So I only can calculate delta H's, but since I started at my reference, the delta H is equal to the enthalpy value that I will put into the table. I will fill the table up with these C sub P delta T's. Okay? Then I just plug this heat of reaction into that heat of reaction formula. I add up all the flow rates and enthalpies in, minus all, add up all the outs, minus all the ins. Right? So that's just a plug and chug stage. Now let's do the heat of formation. So the delta H from the reference state to 1000 degrees C is going to be the enthalpy value that I put into the table minus the enthalpy of my reference. This is 0. But my starting point is different. I'm starting now with the atomic species. I first need to create the molecules. So what I'm going to do is say delta H formation of species I. Then I'm going to heat them up from 25 to 1000 heat capacity dt. Feeling good about this? Yes or no? Good. So the last step to put this all together is now we would fill out these enthalpy values here into this table. So I'm just going to write out the expression and see what pops out. So my Q is equal to the summation of the outs minus the summations of the in. So first we're going to have carbon monoxide, 1 carbon monoxide, open brackets here, delta H formation, carbon monoxide, plus integral from 25 to 1000 C sub P carbon monoxide dt, plus hydrogen, 3 delta H formation of hydrogen. Now we know that's equal to 0, but who cares? Let Excel calculate the 0. plus integral 25 to 1,000 C sub p hydrogen dt minus our methane, methane is 1, delta H formation of methane plus integral from 25 to 1,000 heat capacity of methane dt minus 1 for the water, delta H formation of water plus integral from 25 to 1,000 heat capacity of water dt. Okay. Do we see any similarities between the heat of reaction and the heat of formation approach?
They both use the integral with the heat capacity.
Right, so this side here, this is the enthalpy that I will use in the reaction method, right? Heat of reaction method, this is my enthalpy, going from 25 to 1,000. What do all of these terms add up to? That's the heat of reaction. So this is the delta H of reaction at the standard state, right? 1, 3, those are the stoichiometric coefficients for carbon monoxide and hydrogen. -1, -1, those are the stoichiometric coefficients for the methane and the steam. So these two equations are exactly the same. All that differs is where do I want to put the heat of formation information. Helpful? Not helpful? Question.
So the heat of reaction for the enthalpy of the reaction for the heat of reaction method, we're using the reference state at 25 degrees Celsius for our the heats of formation at 25 degrees Celsius to find the heat of reaction. Is that?
Yes. So the way that we are conceptually doing the heat of reaction method is we have all of our reactants at 1,000 degrees. We're going to cool them down to 25 degrees C. That's going to be a negative delta H, right? Because I'm taking energy out of the system. Well, that's why I have minus at this part. Okay? Then I'm going to react the system at 25 degrees C. That is going to be the delta H of reaction at the standard state 25 degrees C. Then I'm going to take the products and I'm going to heat them from 25 to 1,000. That's why my products are positive. That's a positive enthalpy input. Don't overthink this, right? The positives, the negatives, let the math take care of it for you. If the integrals, right, are flipped, like when I first introduced this concept, we went from 1,000 to 25, and they were positive, but don't worry, flipping the signs, it cancels out the negatives. Yeah, question?
So I think you've already said this like 3 different ways, but I'm so confused if you have. But so this, what you have on the bottom right board, that is the heat of formation.
This is the heat of formation method, but it's also the heat of reaction method. It's both of them.
Okay. So what's missing?
So, I will tell you that the only differences between these two methods, okay? If I take this 1 and I erase these brackets and I put a 1 here as well, that's the heat of reaction method.
Only for the top one?
For all of them.
For all of them.
If I follow through in all of them. And if I put the brackets back and I take this 1 and I put it here, that's the heat of formation method. It's the only difference, right? So what I'm doing, okay, is I'm just factoring, I'm just breaking this term here, okay? This term right here is the summation of the stoichiometric coefficients times the heat of formation. Now in this example, it's very clear to see that the stoichiometric coefficients are exactly the number of moles of all the species. So if I just take this stoichiometric coefficient and the heat of formation and I redistribute it into those terms, I've converted from the heat of reaction method to the heat of formation method. Yes?
So in the end, we should get the same result with that.
Absolutely. Doesn't matter.
Why can't we just,
You choose whichever one you like. It doesn't matter to me. I'm just giving you the options.
not on the home computer?
Well, yes, because I want you to, but on the exam, it'll be, well, no, I think I dictate on the exam. But in the real world, you can choose. Yes?
Why do we have both of them if they're the same method?
Because conceptually, the heat of reaction method is what you've all learned already.
Okay.
Conceptually, this is how you've done it. This is how they would think about it in chemistry classes. This method here is very useful to answer the question, what is the heat of reaction of this system at 1,000 degrees C, 700 degrees C, 500 degrees C? Right? So this allows you to get that sort of number and kind of help out a little bit. But in my life, I would always just use this one here. I would always just use the heat of formation. For your project, always use the heat of formation.
So that's what's on the exam then too, right?
Well, there might be a little bit. So here's the thing, though. I could ask you, what's the heat of reaction of this reaction at 400 degrees C? And I can give you some arbitrary reaction. You need to understand the differences between these to know, okay, how do I actually get the heat of reaction at 400 degrees C? So choosing the pathways is sort of necessary to make sense of that. So the heat of reaction method is the most similar to what we've already done in the class, which is, if I ask you for the heat of vaporization at a certain point, you have to heat and cool the liquid to a point where you know what the vaporization energy is, and then heat and cool the vapor. That's exactly what's going on in the heat of reaction method. So maybe when Felder wrote the book that I'm following, he thought that students would take a liking to this one, right? It's conceptually more challenging. This one is conceptually trivial. But if you don't understand the heat of reaction method, you will struggle to do most any enthalpy calculations in the class. Because this is exactly the same as the quiz we did last week, where we only had maybe a third of the class getting it right. What is the heat of vaporization of benzene at a certain condition? That is exactly the same procedure that we're doing here, but instead of vaporization, it's a reaction. So I would highly recommend that you all individually go work this out if you're confused about it. Write it out in your own algebra. Manipulate it in different ways. Solve some of the homework problems both ways. And convince yourself that this is the same thing, and convince yourself why this equation is written this way and why this equation is written this way. But this one here is very easy. I know students like to just have an algorithm that they can download in their brain and then spit out, right, and focus on rote memorization. This one's a good rote memorization approach. This one focuses on choosing and understanding the paths. So that's why I have both. There's a question back here.
So for organization, is the only difference in the tables that like the heat of reaction method has an extent curve or extent column?
Yeah.
Yeah.
Okay. So one question, then I got to switch to someone else.
Is heat of formation not a function of temperature? It's not heat of formation not changing?
This is the heat of formation at the standard state, so that means it's defined to be at 25 degrees C. That one is not a function of temperature. But if I wanted to, let's say, react hydrogen plus 1/2 oxygen into H2O at 500 degrees C, is this the formation reaction? No, because this is not at 25 degrees C. But I could calculate what is the energy of formation at 500 degrees C, and I could just use one of these two strategies that I talked about here. I could cool the hydrogen and oxygen to 25, I could react them at 25, and I can heat the water up to 500. Or I could use the heat of formation, calculate what these enthalpies are here, calculate what this enthalpy is there, and that delta H would be the heat of reaction at 500 degrees C. Okay, so I don't have time to go over this one on the board, but I wanted to show you the possibilities here. So let me drop this down here. Okay. All right. So I want to show you, why is this all messed up here? Here we go. Okay, so this is how I set up my calculation. So this, I have 3 reactions here. So this is propylene oxide synthesis. So propylene C3H6, so that's an alkene, will react with an oxygen to form this triangular shaped compound. This is a really important industrial chemical for polymerization, but it's also a pretty volatile and unstable material, okay? So this is a really, really important industrial process, propylene oxide, ethylene oxide. It's a difficult thing to do, right? Just adding a little bit of oxygen to a hydrocarbon. So what can go wrong? Well, the propylene can just burn, right? So you're having the propylene burning with oxygen to make CO2 and water. We can also have incomplete combustion where the propylene reacts with oxygen to form carbon monoxide and water, right? So we have 3 different possible reactions. So what I've done is I've just created an arbitrary extent of reaction here, right? So let's say reaction 1 is 0.65, reaction 2 is 0.1, reaction 3 is 0.05. So these are all balances that would be determined based on, let's say, a chemical equilibrium constant. It could be based on design specifications, right? It could be based on compositional analysis of the outlet stream, right? So you can deduce what these are based on the material balances. Now, the energy balance can also influence what these are, right? So if I change the temperature of a reactor, I will change the equilibrium constant, which will change the composition, which will change the energy released by the reaction, which will change the equilibrium constant, which will change the composition, which will change the heat of the reaction. So how do I solve that problem? If I change one thing, it changes something else and changes something else. What's that an example of? What? So that's iterative is one way to solve it, but that's just a big complicated nonlinear solution, right? So I could set up an adiabatic reactor, so no heat going in and out. All of the delta H of the reaction will heat up or cool down the process. That will influence the equilibrium constant, which will influence the composition, which will influence the reaction. There will be a global solution to that. It might be difficult to find even with some computers, but that's what nonlinear solvers are for, right? So there's nothing to stop us from combining everything that we've done in the energy balances with everything that we've done in the material balances and actually solving them simultaneously, right? We're just adding one more tool to the toolbox. And you think, why would I ever have to do that? The entire world works that way, right? That's how complicated the real world is. So anyway, okay, so I'm demonstrating here the heat of formation method. So what I'm going to do is I'm going to just, first things first, I'm going to go to the back of the book and I'm just going to look up all my numbers, right? Because this part here is independent of how much each of the reactions go. I even added in the possibility that my oxygen comes from air as opposed to a pure oxygen stream. So in my calculations, you'll notice this is the template that I've provided that I don't know if anyone uses, but I format my cells so I say, hey, Michael, make sure you didn't type these numbers in wrong, okay? So I type these numbers in exactly as I see them from the book because that saves me time in troubleshooting. And you notice that I've made little notes here, just like the book, that these are times 10 to the 12, times 10 to the 8, and blah, 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 and so on and so forth, okay? The order that I put them in is exactly the same as the order for my table down here. So I have a couple of different things. What's my reference temperature? I never want to put numbers into an equation cell in Excel. Only variables. Define all your numbers somewhere else so that you can troubleshoot it quickly. Excess oxygen, I just put this in there to help me do my material balance. You could do it pre-calculated ahead of time. This is just some fancy work where I just ask whether or not I have nitrogen in the system, right? So then I have my reference temperature, my final temperature. I think in this example here, I have the propylene being fed at 25 degrees C. I have the oxygen being fed at 200 degrees C, which means that if it's coming from air, that the nitrogen's also 200 degrees C. I could feed every single thing at different temperatures, doesn't matter, okay? So then what I do is I feed in my initial flow rates of all the species. So I'm choosing a reference of 1 mole of propylene. According to my 100% excess oxygen, that will result in 1 mole of oxygen. You'll notice this is formatted as input cells. This is formatted as a calculation because I'm determining this based on my excess oxygen. So if I wanted to resolve this with 120% excess oxygen, I could do that. Don't have to change anything, okay? The nitrogen, if I change this cell to a 1, that'll populate it with how much nitrogen there is compared to the oxygen. That all makes sense, right? This calculation here, my mole fractions, not strictly necessary for this problem, but let's say I had to do an equilibrium calculation in addition to this. Then I could also use these mole fractions and put it into a K equals Y1, Y2, Y3, Y4. You know what I mean? Temperature in, I'm telling the system what my inlet temperatures are, and then I'm calculating my enthalpies. So these enthalpies here, man, this projector really hates my computer. Let's go, let's go. Right, big, long, nasty equation. B8, that's the heat of formation, and then all of this stuff here is the heat capacity calculation integrated, right? So the first term was times 10 to the minus 3, the second term was 10 times 10 to the minus 5, third term times 10 to the minus 8. So I'm accounting for all of that in this part right here. So when I troubleshoot, did I type that equation incorrectly? It simplifies my troubleshooting. Now, since I have everything organized in the same format, I just drag and drop and I copy this same equation, right? Carbon dioxide, oxygen, oxygen. Do I simplify my algebra? No. Let Excel simplify my algebra. Heat of formation of oxygen, 0. So what? Let Excel calculate 0, right? So it's all very algorithmic. So then I convert from my kilojoules per mole to kilojoules. So I do my summation of the flow rates and enthalpies right here. That's the summation of the N times H in. Good so far? Then I have a table of my stoichiometric coefficients for each of the 3 reactions. In reaction 1, propylene is being consumed in all 3 of them. In the combustion reaction, right, oxygen's being consumed, right, and so on and so forth. So these are just these 3 chemical reactions converted into the stoichiometric coefficients. Then, based on my extensive reaction for them, I calculate what my final number of moles is. I calculate my mole fractions to double check, and I do the same thing, but instead of the inlet temperatures, I choose a final temperature, right? In this case, I chose 700 degrees Celsius, right? Oh, please, projector, you're killing me, right? Same equation, but instead of integrating to the inlet temperatures, I'm integrating to 700. Make sense? Okay, so everything is already solved for me. If I want to run this process at 700 degrees C, I have minus 238 kilojoules per mole of propylene reacted or fed to the process. Okay, you know what? I want to run this at 1,000 degrees C. 194. Okay. Wait, at what temperature would this get at when I have no heat going out? Let's say 1,500 degrees C. Now that number's going down. So what if I wanted to run this adiabatically? What do? Well, I set goal seek, tools, goal seek, set this cell equal to 0. My Q is equal to 0 by changing my final temperature. And if I run this adiabatically, it gets pretty hot, 2,200 degrees Celsius. That is an adiabatic reactor. So my material balance, completely independent from my energy balance. I can arbitrarily change the extent of my reaction. I can arbitrarily change the inlet and outlet temperatures. And guess what? My energy balance, done. Just like that. Right? So in the last problem of your homework, and I'm sorry we're running over a few minutes, the last problem of your homework asks to solve this in an adiabatic process. Okay? That means doesn't matter. Just do a goal seek at the end if you build your table in an organized fashion. Now, let's say, for example, I was running this as an adiabatic reactor, but instead of oxygen being pure, I have nitrogen, right? So that's how much nitrogen would come with 1 mole of oxygen. Now let's do the goal seek one last time and see what the temperature changes. Do you think it'll go higher or lower? Higher or lower? Who votes higher? Who votes lower? Okay, we have like 6 people voting. Okay, set it to 0 by changing this cell, and it would be 1,300, much lower. Because the nitrogen molecule will steal some of that energy, right? So it won't heat up quite as much. So that's why the temperature's lower. It's a dilutant. Okay. Set up your tables like this, and you will be surprised how trivial all of the homework problems become. Be organized, set it up to troubleshoot, and keep it consistent, and then one table can be used to solve virtually all of the reaction balances problems. All right. See you guys all on Monday.